Alright, so in this video I'm gonna be explaining another important paper with the title Understanding Pooling in Graph Neural Networks. This paper in 2021. Inspired by conventional pooling layers in convolutional neural networks, many recent works in the field of graph machine learning have introduced pooling operators to reduce the size of graphs. The great variety in the literature stems from many possible strategies for coarsening a graph, which may depend on different assumptions on the graph structure or the specific downstream task. So they propose a formal characterization of graph pooling based on three main operations called selection, reduction, and connection, with the goal of unifying the literature under a common framework. Following this formalization, we introduce a taxonomy of pooling operators and characterize more than 30 pooling methods proposed in recent literature. So we show that graph pooling operators can be seen as a combination of selection, reduction, and connection. This is the schematic view of pooling operators. The selection function groups the nodes into supernodes, S1 through S sub k. The reduction function maps each supernode to the attribute of node k in the pooled graph. Finally, the connection function computes the edges between each pair of new nodes. So the SRC operations allow us to easily describe pooling methods. So we define a pooling operator as any function like pool that we have a graph, it provides a graph. So it's a composition of selection and reduction and connection. The selection function maps the nodes of input graphs to nodes of pooled one. But the reduction computes the node attribute of graph G prime by aggregating the node attributes of G selected in each supernode. And the connection function determines for each pair of supernodes the presence or absence of an edge between the corresponding nodes K and L in the pooled graph. So we can see SRC as embedding operations. Since three SRC functions are essentially node and graph embedding operations, we can rely on well-established theory to study expressive power of pooling operators when formulated under the SRC framework. So consider a graph space defined on compact node and edge attributes. K of G is the number of nodes of G prime. Now G of S sub k, because we can interpret cell as permutation equivalent node embedding operator. So G sub sk indicates an augmentation of G such that its node features are now X of S sub k. So this is a concatenation of both of them. It is immediate to see that the augmented graphs are an equivalent way of representing the inputs of reduce and connect. So by implementing cell, we can see it's a universal equivalent network, as is defined here in this reference. And reduce and connect are universal invariant ones. The cell is universal equivariant one. These two are universal invariant ones. Now you can see different select, reduce, and connect for different popular methods that I've explained. For example, diff pool, top K pool, sag pool, min cut. I've explained these in different videos, so you can compare how different they are by just seeing different composition of connect and reduce and select. For example, the connect part of diff pool and min cut are completely the same, but the reduce part is different because diff pool is another GNN. That's why we say diff pool has large computational complexity. Or even the select part of diff pool is very bad because it adds another GNN, but for min cut it's just the MLP layer. So it is possible to distinguish pooling methods according to the number of nodes of the pooled graph. If k is constant and independent from input graph size, we say the pooling method is fixed. A distinction often found in literature is between regular and global pooling, which is extremely evident, to the point where global pooling is usually referred to as a separate operation called readout. So this is a taxonomy of pooling operators that you can see if it is non-trainable, dense or sparse, fixed or adaptive, hierarchical or global pooling. For example, diff pool is hierarchical pooling. It is fixed in advance, and it is dense. It is dense, but top K is sparse. Also, it is trainable. For diff pool, min cut, struct, all of them are trainable. Same as top K, which is trainable. So you see, supernodes, sparse supernodes, have a constant cardinality, while dense supernodes scale with the size of the graph. Now you can see the accuracy of graph classification benchmarks